Hi guys, I hope you're having a wonderful day so far. We are going to talk about subatomic particles. So we've gone through the history of the atom, and we know that atoms are indeed divisible. That means we can divide them or break them down, and the atoms are made up of subatomic particles. Subatomic means smaller than an atom. So inside of the atom we have protons, neutrons, and electrons, and those are made up of quarks. And I would highly recommend that you watch the Quarks song, and there's a couple of videos about quarks in the fun videos folder. So we all have a periodic table. So if you look at the periodic table, you will find that each element's symbol has a couple of numbers next to it. And each of the publishers of a periodic table can choose where they want to put these numbers. So it is their choice as publishers. However, when we write symbols down in our notes, or when we publish papers, scientists, when they do their research and publish papers, we all have to write the numbers in the same spot, so we all know, how to read everybody's literature. So if you are given an element symbol, and you would have 4 spots where you can see numbers. So we're going to start with this spot right here, which is your atomic number. So the bottom left is the atomic number. The atomic number gets the symbol capital Z. And it's also known as nuclear charge. So we know that in the nucleus there are protons and neutrons. What gives the nucleus its charge is the protons, because remember, neutrons are neutral and the protons are positively charged. So this is actually the number of protons. So the number of protons is equal to the atomic number. Now that atomic number identifies what the element is. So for example, if I have an element that has an atomic number of 8, or I'm given that an element has 8 protons, that means no matter what, it's going to be oxygen. That number is what identifies what the element is. So if there are 8 protons, or the atomic number is 8, that means it's definitely oxygen. No matter how many electrons, no matter how many neutrons, it does not matter. This is the number that identifies what element it is. Now let's say I want to figure out the number of electrons. Well, if you have something that's neutral, your positives need to be equal to your negatives, right? And so if I wanted the number of electrons, what I do is I do the atomic number minus the charge. And if an atom is neutral, it does not have a charge, then this is going to be 0. So it's just going to be the atomic number, which makes sense, because if it's neutral, that means the electrons and the protons should be equal. The positives and the negatives should be equal. Now, if it does have a charge, the charge will be written right here. That's where the charge goes. So if it's a charge of +1, then you do the atomic number minus 1, and so on. Okay? Up here, this is where the mass number goes. And the mass number, also sometimes we call this atomic mass. They're slightly different. Atomic mass versus mass numbers, they're slightly different from each other. Atomic mass gets the symbol A. The mass number is basically the number of particles that give you the bulk of the mass, right? Mass number. And so if you remember, protons and neutrons are pretty massive. Electrons, their mass is like 2,000 times less than a proton or a neutron. So the mass number is really, kind of equal to the number of protons plus the number of neutrons. So if I wanted to get the number of neutrons by itself, I would take the mass number and subtract the atomic number. from it. So the mass number is the protons and neutrons together. The atomic number is just the protons. So if I subtract the two, I get the number of neutrons. So let's try a few here. We'll start with gold. And let's look at the periodic table. Let's find gold on the periodic table. Here it is. So on the periodic table, the number that is smaller, that is your atomic number. So that's 79, that's your atomic number. The number that is bigger, the 196.966569, that is your mass number. So let's go back to our packet and put in our values there. So the symbol for gold is Au. The atomic number we read was 79 from the periodic table, which automatically tells us the number of protons is going to be 79. Since they don't give us a charge, they don't tell us it's an ion or anything like that. We'll talk about ions in a few minutes. That means that the number of electrons is also 79 since there's no charge. The mass number we got from the periodic table, we can round it to 197. And if you don't round it, that's okay. If you want to write it down as is, that's fine. But it should be rounded. If we ask for atomic mass, then you just write it as is. But if we ask for a mass number, usually you round that. So to get to the neutrons, what you do is you take the mass number minus the atomic number, subtract them from each other, and that gives you the mass of the neutrons. Now, let's say you chose not to round your mass number. You still have to round your number of neutrons because you can't have like half of a neutron. So, excuse me, that's 118 for gold. Let's look at Cl. Cl is chlorine. And hopefully you have a periodic table in front of you. If you look at chlorine, you'll see that the atomic number is 17, which tells us number of protons is 17. Number of electrons is also 17 since it's neutral. Take a look at the mass number on the periodic table. It is 35. And so if I take 35 minus 17, that gives me 18 neutrons. Okay, the next thing we're going to talk about is isotopes. You've probably heard of these isotopes in physical science or even 8th grade science. Isotopes I think of as siblings. So some of you are only children. Your parents just have one child. And some of you have siblings. And so similarly, some elements have one type of atom. And then some elements have different types of atoms. They have siblings is what I would say. So isotopes, think of those as siblings. So they are atoms that differ only in the number of neutrons, and therefore they differ in the mass. So let's see how we indicate that. So if I tell you, for example, I have nitrogen, then you would assume that that nitrogen is a mixture of all the different possible isotopes of nitrogen. So nitrogen exists as either nitrogen 14 or 15. There are two isotopes. That number that comes after the name is the mass number. And so again, because they have different number of neutrons, their masses are different. And so we indicate what their mass is by putting a number there. For the symbol, we write the symbol and then we indicate what the mass number is in the upper left corner. So if I just have nitrogen or just N, then I assume it's a mixture of the different isotopes. But if I specify and write nitrogen 14 or nitrogen 15 or write the symbol with the mass number here, then that means I'm only talking about just one of the isotopes. Now, if you look at the periodic table for the atomic number, no matter what, if it's nitrogen, it's always going to be 7. Which tell us the protons are always going to be 7 as long as it's nitrogen. The electrons are the atomic number minus the charge, right? And they don't tell us that there's a charge here, so they're both just 7. For the mass number, if they just tell us it's nitrogen, then we look up the mass number from the periodic table. But if they specify what the mass number is, if they give it to you, then that's the mass number that you write. This is 14. And this one's 15. So then to get the number of neutrons, you take the mass number minus the atomic number. So 14 minus 7 is 7. then 15 minus 7 is 8. So you see that with these two isotopes, they are similar in everything. They have the same number of protons, same number of electrons, but they do differ in the number of neutrons, and because of that, their mass number is different. Okay, let's do helium-3. So you would write He and then a 3 right here. Look up the atomic number of helium on the periodic table. It is 2, which means 2 protons, 2 electrons. The mass number, we don't look that up on the periodic table because they give it to us. It is 3. So 3 minus 2 is 1 neutron. Let's try Cl with a 37. So that would be chlorine 37. Put a dash on the mass number. The atomic number for chlorine is 17 from the periodic table, which tell us the protons are 17, electrons, if it's neutral, is 17. And then for the mass number, since they specified as 37, that's the mass number that we use. We don't look it up on the periodic table if they give it to us. So 37 minus 17 for the neutrons would be 20. Last one we'll do with isotopes. So this is hydrogen 2. So hydrogen-2, also known as deuterium. Atomic number for hydrogen is 1, which tell us the protons and the electrons are 1. The mass number, since they specify which isotope, that's the mass number that you use, so 2. And 2 minus 1 would be 1 neutron. So actually hydrogen 1, so the simplest isotope of hydrogen, the one that just has hydrogen 1 here, that is the only type of atom that does not have any neutrons. It would have 1 proton, 1 electron, and that is it. Okay, atomic mass units. So we know that the protons, neutrons, and electrons, and atoms in general are very, very small. And they are not heavy at all. They have very, very, very small masses. And so we can express the mass of an atom in grams, but it's going to be a very, very small number. And so they decided they're going to come up with a unit that represents a very small mass. So when we describe the masses of atoms, it is a simpler number, a number that is easily dealt with. And so they decided they're going to call that unit atomic mass unit, AMU for short. And since carbon is a very common element, it's in all living things, it's very important. And carbon-12 is the most prominent, most abundant isotope of carbon. They decided they're going to base that atomic mass unit on a carbon-12 atom. So they took a carbon-12 atom and they said, well, it has like 6 protons and 6 neutrons. And so the bulk of the mass is based on these 12 subatomic particles. And so we're going to say that a proton or a neutron is about 1 AMU. And so they're going to take the mass of the carbon-12 atom and divide it by 12. And that would give us close to 1, right, as an AMU. And so an AMU is about the mass of a proton or a mass of a neutron. It's not exactly 1. Here are the exact numbers. So a proton is 1.0073 AMU. A neutron is 1.0087 AMU, so very close to each other, just slightly different. An electron, remember, is 2,000 times less massive than that, so it's 0.000549 AMU. And just to give you perspective, this is the mass of each of those in grams. So, you know, to the scale of 10 to the negative 24th of a gram, or 10 to the negative 28th of a gram for an electron. Just to give you a perspective, a gram is about the mass of an M&M. So think of holding an M&M in your hand. That is about the mass of a gram. So a proton is 1.67 times 10 to the negative 24th of a gram. That's 0.0000023 zeros and then a 1/6. So very, very, very small. And an electron is even smaller than that. So when we look at the atomic mass of an atom, the mass of an atom is made up mostly of protons and neutrons, but also, we take into account the mass of the electrons as well. And so if we want to calculate the mass of an atom, we count up how many protons, neutrons, and electrons there are, and add them all up, add all their masses up. So if we want to calculate the mass of a carbon-13 atom, and we want it in AMUs, here's what we do. We say in a carbon-13 atom, we have 6 protons, we have 6 electrons, and we have 7 neutrons. So we're going to say 6 protons, each of them are 1.673 times 10 to the negative, we're doing AMUs in this one, not grams. So 6 times 1.0073 AMU plus 6 electrons, each are 0.000549 AMU, plus 7 neutrons, each are 1.0087 AMU. Add them all together, and we get that the mass of a carbon-13 atom is equal to 13.1080 AMU. And this makes sense because if it is carbon-13, then the mass of it should be pretty close to 13, right? And that's the difference between the mass number and the atomic number. The mass number is usually a whole number, and it tells us how many protons and neutrons there are. So it's just 13 there. Versus the mass number, the atomic mass is a little bit more exact because it takes into account exactly how many protons and neutrons and electrons and their exact masses, and we add them all together. So just slight difference between atomic mass versus mass number here. Mass number is usually the whole number, rounded number of the atomic mass. Okay, what if we wanted it in grams? So let's calculate the mass of an oxygen-18 atom in grams. So same process, we're going to count how many protons, electrons, and neutrons. So oxygen has 8 protons, 8 electrons, and then 10 neutrons. We take 18 minus 8. So we add up 8 times, and we want it in grams this time. So a proton is 1.673 times 10 to the negative 24th of a gram. And by the way, on the test, you do not need to memorize these numbers. They will be given to you. You just need to be able to use them correctly. And then 10 neutrons, each are, 1.675 times 10 to the negative 24th of a gram. Add them all together. And by the way, when you enter these numbers in your calculator, what you want to do is you want to do 8 and then times, and then you do 1.673, and then what you do is you hit second and then comma, and it shows up like this. What this means is times 10 to the power. So then you do negative 24 plus, then you do 8 times, and then you do 9.11, second comma, negative 28, and then plus 10 times 1.675, and then you do second comma, and then negative 24. This is much easier than doing like times 10 to the caret. So when you add them all together, I got 3.014 times 10 to the negative 23rd. Oops, that's a 23 grams. So that's my answer here. So what we just did was calculate the atomic mass of one atom. And if you notice, we looked at just like one isotope. So if you look at carbon or oxygen, let's look at oxygen. Let's look at carbon. Let's look back at the periodic table here and look at oxygen. The mass of oxygen, it says 15.994. That's not what we just calculated, right? Or carbon is 12.0107. That is not what we calculated. Why is that? Why are these numbers different? Well, what we just calculated was the mass of just one type of isotope. The masses on the periodic table are different because in reality, it's very hard to isolate an isotope. When we think of carbon, when we look out in nature, the things that are made of carbon are made up of a mixture of these isotopes of carbon. Same thing with oxygen. The oxygen that we breathe is a mixture of the different isotopes of oxygen. And so we take that into account when we record the mass on the periodic table. And so the mass that's on the periodic table takes account the mass of each isotope and its abundance. So let's look at an example here. We call this the average atomic mass. That's what goes on the periodic table. And it takes, like we said, into account the different isotopes. So let's look at uranium. Uranium has 3 isotopes. Uranium-238, which has a mass of 238.1 AMUs and has abundance of 99.28%. So most of the uranium around is uranium-238. But we also have uranium-235. It has a mass of 235.0 AMUs and an abundance of 0.71. And then uranium-234, and it has a mass of 234.0 AMUs and abundance of 0.0054%. We want to know what is the average atomic mass of uranium, like the number that actually goes on the periodic table. So here's what we do. We add up the mass of each of the isotopes and multiply it by the abundance of it. So we start with the first isotope. So we say average atomic mass equals, take the first isotope, the mass of it, 238.1 AMU, multiply it by its abundance. Now, if you remember, when you multiply by the percentage, you change that typically to a decimal. So you divide by 100. So 99.28% would be 0.9928. Plus, the next isotope is 235.0 AMUs. Its abundance is 0.71%. So that means 0.0071. And then finally, 234.0 AMUs. And its abundance 0.0054. So if we divide that by 100 to make it a decimal, it would be 0.000054. Add all these together and you get 238.067 AMUs. Now, does that number make sense? It's 238. When we have 3 different isotopes, 234, 235, and 238, why is it 238? Well, that's because more than 99% of it is a mass of 238.1. So your atomic mass, your average atomic mass should be pretty close to the mass of that top isotope because more than 99% of it is that. Okay, last topic we're going to talk about is ions, and there are 2 types of ions. Ions means charged particles. There are 2 types of ions. There are cations and anions. So cations are positive ions. Anions are negative ions. One way to remember that, there's many ways, is that cat, the T or cation has a T, so looks like a positive sign. When you write a lowercase t, this looks like a positive sign. The other way to remember it is that cats have paws, right? Cats have paws, positive. Cat, positive. Anyway, so cations are positively charged ions, anions are negatively charged ions. Now, how do these atoms become ions? How do they become charged? Well, they lose or gain electrons, right? It's the electrons that are transferred that cause them to be positive or negative. And so let's think about this. Electrons are negatively charged, right? So if I lose some electrons, if I lose some negatives, I become more positive. So that means these lost electrons. So if you lost electrons, you become a positive charged, and it's a cation. If you gain electrons, gain a negative, that means you become a negative ion, and you're an anion. Now, just so you know, there are polyatomic ions. These poly means many, and so this means many atoms bonded together, which means like, you know, two or more atoms bonded together with an overall charge. So that means that they are bonded together, and then all together they've lost or gained, you know, some electrons. We will talk about polyatomic ions later, but for now we're going to focus on monoatomic ions. That means ions that are made up of just one atom. So to name these ions, you write the element name followed by the word ion. So for example, Na plus would be sodium ion. When you name the anions, the negative ions, you write the element name but change the ending to "ide", then you write the word ion. So for example, F minus. F is fluorine, so instead of calling it fluorine, we call it fluoride ion. Oxygen would be oxide ion. Nitrogen would be nitride ion, and so on. Okay, the other thing we want to do is we want to look at the periodic table and be able to tell what the charge is of different families on the periodic table when they become ions. I think you've studied this probably in physical science or in previous science classes, but let's review it. If you remember, group 1, so hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, group 1, has one valence electron. And remember that these atoms want to lose or gain electrons to become stable, like the noble gases have a noble gas configuration. And so like lithium would, to become like a noble gas, can either lose an electron to become like helium or gain 7 to become like neon. Right? You go 7 boxes this way to become like neon, or just lose 1 box to become like helium. Easier to lose than 1 to gain 7, and so it ends up losing 1 electron, and electrons are negatively charged, and so it becomes +1. So for group 1, they get a +1 charge. Group 2, so beryllium, magnesium, calcium, strontium, barium, and radium. Those have 2 valence electrons, and so easier to lose 2 than it is to gain 6. If they lose 2 electrons, they lose 2 negatives, they become +2. We're going to skip all the transition metals, and we're going to go to the boron family. So the boron family has 3 valence electrons, easier to lose 3 than it is to gain 5. And so when they lose 3, they become +3 charged. Carbon family, so carbon, silicon, germanium, tin, lead, and so on. Those have 4 valence electrons. So if you lose 4 or gain 4, it's just as easy, right? So they are either plus or minus 4. We'll talk more about that later. Usually if it's a metal, it will lose to become positive. If it's a non-metal, it usually gains to become negative. Let's look at the nitrogen family. So nitrogen, phosphorus, arsenic, antimony. Those have 3 valence electrons. So now, or sorry, they have 5 valence electrons. I apologize. So 5 valence electrons. So now it is easier to gain just 3 than it is to lose 5. And so nitrogen and its family, they gain 3 electrons. Well, if they gain 3 electrons and electrons are negative, then that family becomes a -3 charge. The oxygen family has 6 valence electrons, easier to gain 2 than it is to lose all 6, so it becomes -2. The halogens, the fluorine family, they have 7 valence electrons. Much easier to gain 1 than it is to lose all 7, so they become -1. And then the noble gases usually don't really lose or gain electrons because they're already stable. So we're going to use this to be able to tell what the charge is of different elements. So let's try here. So nitride ion. Nitride, where do you think that comes from? Nitride comes from nitrogen. So nitrogen is right here. So we said on the periodic table, it goes +2, +1, +2, +3, ±4, -3, -2, -1. So nitrogen, the nitrogen family is -3. So nitride would be N with a 3-. You put the charge in the upper right corner. Okay, potassium ion, what would that be? Well, potassium is in group 1 right here. So K, and then it becomes +1 because it's in group 1. They get a +1. Okay, next one is sodium. Where is sodium? Sodium is right here. What's the symbol for sodium? Na. Does it say ion? No, it doesn't. So they tricked us. It's just sodium, neutral sodium. It doesn't say ion. If it was sodium ion, it'd be Na+, but just sodium would be Na. Okay, next one, aluminum ion. Where is aluminum? Aluminum is right here, and so that gets a +3 charge. So Al3+. Sulfide ion. Sulfide comes from sulfur right here. So -2. And silicon ion. Silicon is in the carbon family. Right here. So remember we said that that is ±4, right? Well, how do we know? We know because it's a silicon ion as opposed to silicide ion. So it must be a positive, and so it's +4. Okay, let's do the names. So Br-, that's a negative ion, so you end with ide, so bromide ion. W, that is just tungsten, and it doesn't say that it's an ion, so just tungsten. Same thing with Ca. Ca is calcium, does not say ion, so no charge. Or sorry, does not have a charge, so no ion. Cl-, this is chlorine, so we would end it with ide, so chloride ion. Next one is C4-, so that is carbon, so change the ending to ide, so carbide ion. And Cr2+, that is chromium ion. Okay, let's try some where we actually find the number of protons, neutrons, and electrons. So oxide ion. Oxide comes from oxygen, and because it's an ion, we put the charge of it. Check which family it is. You'll see that it's -2. The atomic number is 8, which tells us it's 8 protons. Now let's look at the electrons. This is not neutral, right? So electrons. If you remember how to find the number of electrons, you do the atomic number, which is 8, minus the charge, which is -2. So that gives you 10 electrons. Mass number for oxide, you check oxygen on the periodic table. Mass number is 16, and so 16 minus 8, that gives you 8 neutrons. Let's try cesium ion. So cesium is in group 1, so what charge does it become? +1. So the atomic number for cesium is 55, which tells us it is 55 protons. For the electrons, you take the atomic number, so 55 minus the charge is +1. So that would be 54. And the mass number you get from the periodic table, it is 133. So 133 minus 55, that gives you 78 neutrons. The next one, barium ion. Barium is Ba. It is in group 2, so it gets a +2 charge. Atomic number for barium is 56, so that tells us 56 protons automatically. For the electrons, you take 56, subtract the charge, which is +2, so that would give you 54 again. The mass number from the periodic table for barium is 137. 137 minus 56 is 81. Next is chloride ion. So chloride comes from chlorine, which is Cl. It's in group 17, so the charge of it would be -1. Atomic number for chlorine is 17, which tells us automatically there are 17 protons. For the electrons, you take the atomic number, so 17 minus the charge, which is -1, so 17 minus -1 is 18. For the mass number, you check that on the periodic table, and it is 35. So 35 minus 17, that is 18. Next one, Mg2+. So Mg2+ is magnesium, and to name the ion, because this is positively charged, you just write the name of the element and follow that by the word ion. So just magnesium ion. Okay, the atomic number is 12, which tells us that the protons are also 12. For the electrons, we take the atomic number, which is 12, minus the charge, which is +2, so that gives us 10. For the mass number, it is 24 from the periodic table. 24 minus 12 is 12 neutrons. Next one is P3-. So P is phosphorus, but we need to change the ending to "ide", so that would be phosphide ion. So phosphide ion. The atomic number for phosphorus, I believe, is 15, which tells us 15 protons. If we want to find the number of electrons, we take the atomic number, which is 15, minus the charge. The charge is -3. And so that gives us 18. The mass number of phosphorus from the periodic table is 31. So 31 minus 15 would give you 16 neutrons. Just a little thing here with the numbers and the charges. Usually when it, like let's say it's -3 charge, we usually say -3, but we write it as 3-. If you wrote it as -3, that is totally fine. That's just how we write it next to the symbol, just out of habit or tradition. That's the more correct way to write. Okay, the next one's really tricky. So it looks like it's hydrogen, and it's positively charged, so ion, but it's not just a mixture of hydrogen, it is a specific isotope of hydrogen. It is hydrogen 2, but it's also an ion. So here's the name of it. You'd write hydrogen, but we're talking about just hydrogen 2, so hydrogen /2 or -2 and then ion. Okay, atomic number for hydrogen is 1, which tells us protons are also 1. To get the number of electrons, you take the atomic number, which is 1, minus the charge, which is +1. So 1 minus 1, oh, it has no electrons. How interesting. The mass number you get not from the periodic table, but from here, because they give it to you, so that's a 2. 2 minus 1 would give you 1 neutron. Last one we have here is sulfur, but it's an ion, so we need to change it to ide, so sulfide ion. But also it is a specific isotope, it's not just a mixture of sulfur. So this would be sulfide 32 ion. The atomic number for sulfur is 16, which tells us 16 protons. For the electrons, we take the atomic number, which is 16, minus the charge, which is -2, so that gives us 18. For the mass number, that is 32, that's given to us, not from the periodic table, but given to us right here. And 32 minus 16 would give you 16. So remember that we said that the atoms lose or gain electrons to become stable, like the noble gases, right? So what I want you to do is I want you to focus on the number of electrons right here. 10, 54, 18, 10, 18. Ignore that 0, 18. Okay, now I want you to look at the periodic table and look at the noble gases that are stable. Now, if these are, the atomic number remembers the number of protons, it's also equal to the electrons when it's stable, right? Or when it's neutral, I mean. So helium, being neutral, would have 2 electrons and 2 protons, of course. Neon would have 10. Argon is 18. Krypton is 36. Xenon is 54. If you look at all the number of electrons, look, 54 is right here, 18 is right here, 10 is right here. Now look back at what we have. 10, 54, 18, 10, 18. So most of the time, not 100% of the time, but I would say about 90% or more of the time, when you are trying to figure out how many electrons are in an ion, it is likely that it's going to be one of the numbers that's on the noble gases. It's going to be one of those numbers, 2, 10, 18, 36, 54, 86, or 118. Because the whole purpose of them losing or gaining electrons is to become like these noble gases because they are stable. So that's pretty cool, and it's something to kind of keep in mind. So if you're doing like oxygen, for example, like oxide ion, and you're trying to figure out, ooh, do I subtract the 2 to make it like 6, or do I make it 10? What do I do? Most likely, it's going to be one of the numbers on the noble gases, and so it's going to be 10. So that can kind of like help you as well. All right, I hope you guys have a wonderful rest of your day. Bye.